Hello and welcome to a Maths with Harry lesson. In this video, we're going to be having a look at the discriminants. I'm going to start by reintroducing to you the quadratic formula. Now, you've seen this in previous videos of mine, and you've probably seen it at GCSE as well. This is the quadratic formula, and as you probably know, the quadratic formula solves quadratics in the form ax squared plus bx plus c, okay? And equal to 0, we can solve the quadratic, okay? Now, just so you know, this isn't actually part of this video, but just so you know, the quadratic formula actually comes about by completing the square on this form of the quadratic, okay? So that's how we actually get the quadratic formula here to be equal to x. That's just a little bit of extra knowledge. Now, today in this video, we're going to be having a look at the discriminant. So first of all, we need to know what on earth is the discriminant. The discriminant is part of the quadratic formula, and I'm going to highlight which part it is. It's this part under the square root, and we'll label it here. That is the discriminant. So the discriminant is b squared minus 4ac. Now, the discriminant can be one of three things, okay? When we put values of a, b and c in, it can either be equal to 0, it can be less than 0, or it can be greater than 0, okay? And under this little box there, I've got 3 copies of the discriminant, and we said it can be equal to 0, it can be, and in fact I'm going to write greater than 0 first, and then less than or equal to 0. Okay, so those 3 things there, those are the 3 kind of situations of the discriminant. Equal, less than, or greater than 0. Okay, now those 3 situations determine whether we can find solutions and how many solutions we can find of a quadratic. If our discriminant is equal to 0, then what that means is we're taking the square root of 0. Okay, so we're taking the square root of 0, so it's just going to disappear here. And in the case when b squared minus 4ac is equal to 0, we get 1 repeated root. Okay, now before I start writing any of this down, what on earth is a root? If you've seen previous videos of mine, you'll know what a root is, but let's write down the definition. A root of, let's say, f of x is equal to ax squared plus bx plus c, okay, just the general form of a quadratic. The roots, or I should say the roots actually, because there's always going to be 2. The roots of f of x is equal to ax squared plus bx plus c are the x values that satisfy f of x is equal to 0. Okay, so in other words, if we think about it in terms of a sketch of a quadratic, it's where the quadratic or the curve intersects the x-axis, okay? If we put a value of x into here, it's a root if we get f of x is equal to 0, okay? Now, what I just said a minute ago is if we've got our discriminant equal to 0, what we get is, and I'll write this as a red little semicolon here for all of these, what we get is we get 1 repeated root. Okay, now a root, remember, is a solution to the quadratic equal to 0. That's what I just said. Now, in a previous video, I also mentioned that a quadratic always has 2 roots, okay? It always has 2 roots. And the reason for that is because the quadratic here has the highest power of 2, so it's always going to have the same number of roots, or solutions, I should really say, as the highest power, okay? So when it's equal to 0, we have 1 repeated root. So for example, we might have the root 1, but we have it twice, okay? It's one root, but it's repeated twice, okay? A little bit hard to get our head round, but because we are always going to have two roots, then we know we're going to have the root 1 twice, or the root, I don't know, 16 twice, or whatever. We have that same root, just repeated, okay? Now let's think about if the discriminant is greater than 0. If it's greater than 0, then, well, we're square rooting something that's greater than 0, so that's okay. It's positive if it's greater than 0, so we can do that. And, well, we're going to plus and minus that thing from minus b here on the numerator. So we're going to get two different roots, because we're going to add the square root of our positive b squared minus 4ac. That will give us one answer. Then we're going to get a different answer by minusing, okay? So what we're going to get in that case is we're going to get 2, and I'm going to introduce a key word here, distinct, and I should really say real roots, okay? We'll introduce real roots there, and also real roots we can add on there. Real roots meaning they are a number, they exist, and we can think about them as a real number. Okay, so distinct here means they are different. We have two roots and they are both different. Okay, that's when b squared minus 4ac is greater than 0. And you've actually been doing that when you solve quadratics. You might not have just realised it. If you have a positive number under this quadratic, you're going to get two different solutions or two different roots, because you're going to add the square root to get 1, and then you're going to take the square root to get a different root. Okay? Now, what happens if b squared minus 4ac is less than 0? We had an example like this in the previous video. We had minus 8 under the square root when we were solving the quadratic to graph it. So we couldn't really do anything with that. And the reason we can't do that is because in real world, we're not able to square root a negative number. If you think about it, try and give me a number that multiplies by itself to give me a negative number. Well, let's think about two positive numbers. That's going to give me positive, so that's not going to work. Two negative numbers also gives me positive. So we're not going to be able to multiply a number by itself that's positive or negative to give me a negative number. Okay? So, what happens when we've got it less than or equal to 0? Well, you might think we had one root here, which was repeated. We had two roots here, which were different. Here, we have no real roots. Okay? Now that kind of contradicts what I just said about them always having two roots, but we don't need to get into that. That's further maths, okay? So we just take here at A level that we have no real roots if b squared minus 4ac is less than 0, because we can't square root a negative number. Okay, so now we're going to have a look at how the discriminants can kind of change the shape of the graph, or where the graph of the quadratic lies on the x and y axis. You can see here I have got 3 quadratic curves, and I've also got 3 other quadratic curves. Now they are exactly the same quadratics, apart from we've got, for the top 3, a being positive. Okay, so when a is positive, we get this lovely U-shaped here. And then these 3 examples here is when a is negative, or a is less than 0. What we get is we get kind of this N shape, if you like, okay? Now, each of these come from a equation like this: y is equal to ax squared plus bx plus c. I've just done some random quadratics here. I don't know what a, b and c are. I'm just purely doing these graphs to show you and to demonstrate how the discriminant changes the shape of the graph. So in the first 2 examples here, we've got a being positive and a being negative. We have the discriminant being greater than 0. Okay, and we're going to have a look at these graphs in terms of their roots. Now remember, I just said when the discriminant b squared minus 4ac is greater than 0, we have 2 distinct real roots. And the roots are the x values that satisfy f of x being equal to 0. In other words, it's like I said, where the curve intersects the x-axis. So in these two first examples here, we've got the discriminant being greater than 0. So we are going to have two distinct roots. Okay, and we'll write that in green. Two, and I should say distinct real roots. Two distinct real roots. Okay. Now we can actually see that from the graph that we have two distinct real roots. We can see, and I'll highlight this in green, there is a root there, and there's another root there. And also when a is negative, those are our two roots. And you can see they are distinct meaning different, because, well, this is in the negative part of the x-axis, this is in the positive part, so they must be different. And same for those two roots there. Okay, so that's what happens when we graph a quadratic and the discriminant is greater than 0, we can see that we have two distinct roots, okay? And that's the visual interpretation of what the discriminant tells us. Okay, if we have a look then at when the discriminant is equal to 0. Previously, I just said that when it's equal to 0, we have one repeated real root, okay, or roots, if you want to say roots. So I'll write that here, one repeated real root. So that root appears twice, even though it's the same root, okay? And we can see that, and I remember doing this in another video, from that factorisation of a quadratic curve, okay? We get x equals 1 from this bracket, and we get x equals 1 again. So that is a repeated root. We get x equals 1 as the root, but we get that root twice, okay? Now, how does the graph actually kind of interpret that we have one repeated real root? Well, if we zoom in and we look at the turning point, this is the positive value of a graph. If we zoom in and we look at that turning point, we can see, and I'll go back to a highlighter actually, there is our root, okay? That's the only point that intersects the x-axis. Remember, the roots are where we intersect the x-axis. So we can see there that that is our root. And I don't know, that root could, for example, maybe be 2, okay? What we would have is we'd have x equals 2 being a root, but I would say that's a repeated root. And the reason for that is because the turning point is the actual root itself, okay? It intersects at the turning point. So I'm just going to get rid of that example just so we can have the green highlight. And also for the negative, we can see there is the root on the negative. So we can see when we've got a discriminant equal to 0, we get the turning point on the x-axis for both a positive and a negative. Okay? Right, let's have a look then at when b squared minus 4ac is less than 0. This one is a little bit difficult to get your head around if you want to think about it. What we have is we have no real roots. So we'll write that again down here. No real roots, and I'll just write it next to it, for when the discriminant is less than 0. And we can see that for the third time, we can see that the roots are where the curve intersects the x-axis. Well, for our a being positive, we've got this U shape. The curve, this orange curve, does not intersect the x-axis. So where can I kind of highlight my roots? It doesn't make sense. There is no intersection between the x-axis and the curve. So in other words, we have no roots, and hopefully that makes it a little bit easier. Now I've kind of shown you a graphical example of a curve having no real roots. Okay, and similarly, as you can see down here, this is the a being negative, so we get the frown kind of shape. And we can see again, it's not intersecting with the x-axis. This is the maximum point here. The graph's not going to get any bigger. We carry on all the way down here. We could have arrows on like that if you wanted to kind of imply that the graph is continuing down and down. And here, the graph is continuing up and up and up. this is the minimum value of this graph. It's not going to get any more negative or any smaller, so it's not going to intersect the x-axis. So those are the three situations for the discriminant. And we can see that that really helps us think about the roots of the quadratic. Okay? All right, let's have a look at an example then. Example 1 says, find the value of k for which f of x is equal to this, x squared plus kx plus 9, where that f of x has equal roots. So you can press pause and have a go if you think you want to. Don't worry if you don't, I will go through the answer when you press play. Alright, let's have a work through then and let's see what we can do. So again, we need to find the values of k for which this function has equal roots. Equal roots is just another way of saying, and I'll write this in blue, let me make that a straight line. It's another way of saying one repeated root. Okay, because one repeated root signifies we do have two roots, we've just got one root repeated twice. Okay, so equal roots is another way of saying one repeated root. Okay, so what we need to think is, well, we know we've got one repeated root, so let's go back up here. One repeated root means that the discriminant is equal to 0. So I'll write it in blue to match. That implies that b squared minus 4ac is going to be equal to 0. Okay, now this is our quadratic here. I can highlight that in green. That's our quadratic. So we know what a, b and c are. We can say that a is equal to 1. We can say that b is equal to, well, k. Okay, we don't have a numerical value for b, but we do know that b is k. And we know that c is equal to 9, because all I did is compared it to that form of the quadratic, which is just a general form. Okay, so we know what a, b and c are now, so all I'm now going to do, and I'll write it in red, I'm now going to substitute into b squared minus 4ac, because that is the discriminant. So if we do that, well, we'll have b squared, and I'll just write it up here so I've got enough room, b squared minus 4ac will be equal to, b is k, so k all squared, minus 4 times a, which is 1, times c, which is 9, and that is going to be equal to 0 because of this fact here, we've got one repeated root. Okay, so if we simplify that, we'll have k squared, and then we're going to have minus 4 times, and why have I wrote a there? Oh, that's a 9. So we're going to have minus 4 times 9, so that's going to be minus, and then, well, 9 times 1 is 9, 18, 27, 36, so minus 36 there will be equal to 0. Okay, so we've now got rid of, well, we've got rid of b, we've got rid of a, we've got rid of c, and we've now just got our determinants in terms of, a discriminant, sorry, in terms of k. So what we're going to do is we are now going to solve, and I'll write now, we are going to solve for k. Okay? So if we solve for k, well, we've got k squared, and if we add 36 to both sides, we're going to get k squared is equal to 36. And then what we will do is we will square root both sides. When we square root, we're going to get positive and negative. So square root both sides, we'll get k will be equal to plus or minus the square root of 36. So k will be equal to plus or minus 6, because 6 times 6 is 36. Now, what did the question say? Well, the question is always going to be grammatically correct. The question asked us to find the values. Look here, I'll highlight it in red. Values. We were asked to find multiple values, okay? That's why the word is plural. So, that is our final answer. K can be of two things. It can be a positive 6 or it can be a negative 6. Okay, and that is our final answer. And if I check that against the solution, plus or minus 6 is correct. So all we did is kind of use the information here, the equal roots. Well, if we've got equal roots, then we know that that means one repeated root, so the discriminant is equal to 0. And then we can just, from here, find our values of a, b and c, substitute to then solve for k. Hopefully that wasn't too hard. Let's have a look at example 2. Here we want to find the range of values for k for which this function here, x squared plus 4x plus k equals to 0, has, and we'll highlight it in green, two distinct real solutions. And remember, solutions, I'll just underline that properly, solutions is another way of saying roots. So press pause and have a go if you want to, and then press play and we'll work through the answer. Alright, hopefully you had a go at that. Let's work through the answer. The first thing I'm going to do is I'm going to use this information here to tell me that the discriminant, or in other words, b squared minus 4ac, that is greater than 0. Okay? And the reason for that is because that was our criteria at the top here. We had three pieces of information. Greater than 0, we've got two distinct real roots or solutions. Okay, so that's the case. We're going to do the exact same thing again. I'm going to say, in this case, a is equal to 1, b is equal to 4, and c is equal to k. Okay, now notice, this is quite a key word, it says range of values. We want to find a range, okay? And the reason it says range is because, well, we want our discriminant to be greater than 0. We're involving an inequality here, so we need the range of values. We're not going to get equals, we're going to get an inequality, because that's what we're starting with here. Okay, so what do we need to do? Well, I'm going to substitute in. So now let's substitute. Okay, and I'm going to get b squared minus 4ac to be equal to, well, we're going to have b squared, which is 4 squared, minus 4 times a times c, and we want that to be greater than 0. Greater than 0 from that there, okay? So then I can say, well, that is 16 minus 4k is greater than 0. And then, well, if I get rid of that equals sign there, so there we go, oh, got rid of the 1. If we get rid of that equals sign so it doesn't confuse you, that is just now a normal inequality that we've been able to solve for years, okay? We just need to solve it like a normal equation. So the first thing I'm going to do is add 4k to both sides to give me, and I'm going to write it the other way around. 4k is less than 16, okay? Adding 4k to both sides gives me, and I'll write a little arrow, it gives me that, and then if we flip it the other way around so that the 4k comes over here and the 16k comes over here, we need to flip the sign, and it gives me 4k is less than 16. And then all I'm going to do is I'm going to divide by 4 on both sides to give me k being less than 4. Okay? And that is my answer. That is a range of values. We wanted the range of values. We're not going to get an equals because it's two distinct real roots. So we're going to have an inequality for our discriminant. And then we can see we arrive at k is less than 4. And checking with the solutions, that's what we should have got. Okay, so hopefully that makes sense. All right, final example for this video. Pause and have a go at this one. We've got a function h of x being equal to 2x squared plus k plus 4 all multiplied by x plus k, where k is a real constant. What we need to do is we need to find the discriminant of h of x, and then we need to prove that h of x has two distinct real roots for all values of k. So pause and have a go at that if you want to, and then we will work through the answer. Okay, hopefully you paused, and let's see whether your answer was correct. So we need to find the discriminant. It doesn't tell us anything about the discriminant, so all we need to do is just find it, okay? We know that the discriminant is b squared minus 4ac, and if we don't read part B just for the minute, looking at part A, we just need to find the value of that, okay? So all we need to do is we need to substitute. So b squared, well, let's first of all write down actually what a, b and c are. We can see that a, well, I'll highlight that in red, is 2. We can see b is k minus 4, and we can see that c is k, okay? Oh, k plus 4, sorry, did I say minus? Okay, so a is 2, b, I'll write in green, b is equal to k plus 4, and then again in grey, c is equal to k. So substitute, I'll just write sub, b squared minus 4ac will become k plus 4 squared minus 4 times 2 times k. That is, well, we can expand those brackets to give us k squared plus 8k plus 16 minus, and that gives me 8k. Okay, then we can simplify. We can see that, well, that is going to cancel with that, so those two terms are going to disappear, and I am just left with k squared plus 16. So that is my discriminant. We were just asked to find it, okay? All we needed to do was just substitute a, b and c. Part B then said hence or otherwise. So we could use part A, or we could do it another way. Prove that h of x has two distinct real roots for all values of k. Well, b squared minus 4ac we just worked out. The discriminant is k squared plus 16, okay? We'll write it in grey. To have two distinct real roots, b squared minus 4ac must be greater than 0, okay? Because that was one of the criteria we had at the start. So to have two distinct real roots, what we need is we need this to be greater than or equal to 0 for any value of k. I am going to have a look at the two terms separate. We'll highlight one grey and we'll highlight one red. Let's think about k squared, okay? K squared is a square function. We put in k and we then square it and get an output, okay? Anything we square is always going to be positive, because if it's a minus number that we put in, minus times a minus gives me a plus. So k squared is always greater than or equal to 0 for all values of k. And you might have actually seen at GCSE that if we want to graph, and let's just make that a straight line, if we want to graph y is equal to x squared, okay, we get this. And I can't make that any neater, I don't think it's going to, oh, there we go. That is y equals x squared. So actually, it can be equal to 0 as well. I should put that on there because it could, you know, be at that turning point there. But that's the graph of y equals x squared. So if we didn't have x and we just had k, then k squared is always greater than or equal to 0 for all values of k that we put in there. Because we can put k being equal to 0 in, and that will give us k squared equals to 0. Okay, so that's the case for k squared. What about this plus 16? Well, if we plus 16, we know 16 is greater than 0, okay? And that's just a fact. 16 is a constant, it's always going to be greater than 0. And so we can then say that because we've got something that's always greater than or equal to 0, plus something that's always greater than 0, the 16, k squared plus 16 is always greater than 0 for all values of k. Okay, because if, for example, we do have k being equal to 0, then this term will disappear because it will be equal to 0, but we're just left with the discriminant as 16, and that's still greater than 0. And so we have two distinct real roots for all values of k.